So good afternoon, everyone. First of all, I shall thank the organizers for giving DFCCIL an opportunity to present the work being done in DFCCIL. My work is the presentation is basically on electrification progress in dedicated freight corridor in terms of what are the systems being deployed in DFCCIL for electrification, what are the power supply arrangements, sources of energy, what are the timelines of the project for various corridors, and what are the future prospects for the suppliers of equipment in India. So that is the major basic content as given here. So if I systematically explain here, first is the overview about Indian Railways, and followed by adoption of technology on DFCCIL, the approach followed for electrification, the 25 kV 80 FET system, because it is a new system in India. Presently, only one small section is having this system in IR, and in DFCC we are deploying the system in a large area. Then the power supply arrangements, targets and timelines, and upcoming tenders and opportunities. I hope my voice is I am audible properly.
Yes, sir, you're audible, sir.
So this is an overview of Indian Railways. Although most of the people will be aware about this, that this is the golden quadrilateral of Indian Railways, Delhi to Mumbai, Mumbai, Chennai, Chennai, Kolkata, mainly connecting these four metros. So these are basically high density corridor, and it's known as golden quadrilateral diagonals also, because this is the 16% of our route kilometer of Indian Railways, and it carries approximately 52% of passenger and 58% of freight traffic. So that is why it is golden quadrilateral, and it is highly congested. You can imagine 16% route carrying 58% of traffic of complete IR. So now, what are the concerns for Indian Railways regarding freight traffic? The market share of Indian Railways was decreasing from 90% to 30%, mainly because the capacity constraints are there on this high density network. Main reason is because passenger trains are also plying on the same route where goods trains are plying. So due to this differential speed of trains, one hand you are having Rajdhani of 130-140 km, and goods train is having average speed of 25. So the differential is so much that it creates delays in movement of freight trains, and due to this we are not able to increase the capacity. Then there are inadequate ports connectivity in the present system, inability to carry longer, heavier trains, and this is all resulting in the lower throughput in the system. So to avoid this and to increase the freight capacity, government has decided to have two freight corridors. One is Eastern Corridor, and that is runs from Ludhiana up to Dankuni, including PPP section from Sonnagar to Dankuni, and another Western Corridor around 1500 kilometers. It runs from Dadri and it goes up to JNPT, mainly the western side it covers. So the objectives of the project I will not discuss in much detail because time limit is only 20 minutes. So our objective is that first of all to increase the rail share in freight traffic, which is falling in last so many years, and then to create additional rail infrastructure to cater to high level of transport demand, because demand is increasing day by day. So we have to cater to the increasing demand. Then because there is a competition with road also, so we have to reduce unit cost of transportation. But when we analyze that why rail traffic is going down in terms of freight trains, so this is also one important aspect, that we have to be competitive with the other modes of transportation. So our aim is also to reduce it. And second is that we have to provide seamless, basically end-to-end solution to the customers, because customer will not like that first he will use road and then rail and then again road. So our objective is that he should get an end-to-end connectivity. So these are the basic design features which are different from Indian Railways, because how to increase the freight loading is that first of all we have to change the basic design features of our wagons, like we have increased the height, increase the width of the container stack. Similarly, we are proposing to increase the train length. Right now the train length is around 700 meter, which we will be using up to 1500 meter, that is known as heavy haul train. Similarly, the train load also it will be changed. Right now the train load is only 4,500 ton, and in DFC it will be in the range of up to 13,000 ton. So there will be a complete paradigm shift in terms of loading of trains in the DFC CIL. Similarly, the basic for increasing the loading is that we have to design the system for higher axle loads. At present in Indian Railways, the loading is maximum, it is 22.9 ton, whereas in DFC routes, our system, we will be operating at 25 tons, and in future it will be able to upgrade up to 32.5 ton. So there will be a dramatic increase in the loading. Similarly, the track loading density, all these are design factors. Maximum speed is one. In IR it is 75 kmph, whereas in DFC it will be 100 kmph. So if we come, our main topic of discussion is today electrification. So if we compare with Indian Railways is using so far only 25 kV AC traction, and it has been performing well in terms of requirement and capacity of Indian Railways. So whenever there was an increase in demand, it has been met by slowly upgrading the transformers like from 12.5 MVA to 21.6 or up to 30 MVA. Or in case demand was furthermore, we have introduced some additional traction substations. So this is basically an incremental approach to be adopted for slowly increasing the demand. But in case of freight traffic, what we envisage that this incremental approach probably will not work out, and we have to execute a quantum upgradation of the AC traction system, because there is an increase in axle load, like earlier it was 20 ton, and we will be shifting to 25 ton immediately, and in future it will be upgraded up to 32.5 ton. So if we want an increase in axle load from 20 to 32.5 ton, so there will be quantum upgradation of the complete system. So we cannot go with the incremental change, that is we slightly change the transformer, add one or two switching posts, so it will not work. So for increasing the train haulage capacity or for running the long haul trains and for meeting the train frequency, we have to go for the quantum upgradation. So this has been possible by adopting, as I explained, this increase in axle load and then increase in power rating of the locomotives. At present, the locomotives on Indian Railways, they are having only up to 6,000 horsepower, whereas in DFC CIL, it has been envisaged to use 9,000 and in Western Corridor and 12,000 horsepower locomotive on Eastern Corridor. So again, it will be quantum upgradation from 6,000 to 12,000. So that will enable us to carry increased loading on freight. If you compare with IR, the power capacity on high density routes, it is not more than 1 MVA per RKM. So means in 1 route kilometer, the capacity is only 1 MVA. It is even less than that. Whereas DFCCL, it has been planned to augment the capacity up to 1.5 MVA per RKM, means more than 50% increment on DFCCL. These are the whatever DFCCL has floated the tenders and work is in execution. So we are adopting the use of concurrent technology based on international standards, EN, IEC, and other standards. To adopt new technology, we have followed the cross acceptance criteria in our tenders, and there is an element for transfer of technology also to increase the local sourcing and encouragement for Make in India, because we don't want that everything we should be dependent on the import agencies, because in the long run our local partners have to meet the maintenance requirements, future requirements also. So that aspect has also been taken care for the transfer of technology. These are the main aspects of transfer technology, that the vendors who has to supply the material, he should have a 3 years of satisfactory performance, should have supplied equipment of 70% of rating of equipment and 50% of quantity in the last 7 years. And he can supply maximum 2 times the quantity supply in last 7 years. So these are the guidelines which we have adopted in our tenders for the approval of new vendors who are not approved on Indian Railways so far. So it means we are quite open to new vendors also. If anyone is meeting these criteria, then he can be eligible for approval in DFCCIL corridors. So if we come directly to this 25 kV 80 fed system, because I explained that it needs to be a quantum jump in the thinking process in the system. So for that we have gone for 25 kV AT system, or it is known as 2 into 25 kV system. So what is this system basically? So this is just, I will not go in much detail. This is a just simple diagram to understand for a layman that how is the arrangement. So it shows that the incoming supply in our substations is 132 or 220 kV level, and on WDFC we have used spot transformers in the traction substations. On ADFC we have used V-type connected traction transformers. So on the secondary side we are having a as I shown overhead contact wire at 25 kV and this negative feeder at minus 25 kV. So these are the two feeders at plus 25 and minus 25 kV. These are run along the complete corridor. So that is why the system is known as 2 into 25 kV system, because there are two conductors running at 25 kV plus and minus. So in this system we are making use of these auto transformers 81, 82, 83 and so on. The main advantage of this system is that if whenever a locomotive with train is moving in a particular stretch of the section, the maximum current sharing is being done by only these two auto transformers. So the net current in these conductors is getting reduced because around 50% current is circulating, depends on the location of this train. 50% let us say current is distributed here only. So the total current flowing from the traction substation, it is in the conductors is reduced to a 50%. So we can say that the voltage drop and other associated benefits of the system. As I show the voltage drop comparison here. So in the case of IR where 25 kV system is followed, as we move from the traction substation, the voltage drop increases in a almost linear fashion. Whereas in case of 2 into 25 system, we see that this is a curve being followed for voltage drop. So means for the same distance in 25 and 2 into 25 system, voltage drop is much less compared to this single 25 kV system. So because this voltage drop is less, due to this feature we are able to increase the distance between the two substations on DFC CIL system. So if we summarize these advantages, that our insulation level for equipment is at 25 kV, whereas the voltage drop, the feed is doubled at 50 kV. Therefore, it reduces the current by almost 50%, which leads to distance between traction points at 60 to 80 km. Whereas in case of IR, it is 30 to 40 km only. So improved voltage regulation and power density is more than 1 MVA per RPM. And there are lesser number of power conditioning equipment. Same locomotives can be used which are running on the Indian Railways. There is not much difference. Load factor is improved, and system doesn't not only provides quantum jump of 100% in haulage capacity, but it leaves scope for further capacity upgradation also. So not only we are increasing the capacity by 100%, but there is further scope of capacity upgradation by increasing the transformer capacity, that is operation of transformers in oil natural, air forced or oil forced, air force modes. So if we operate these transformers, again the capacity of the system gets enhanced. So what is the DFC CIL approach for electrification? So I will just skip this slide because of shortage time. This is just gives the project mandate that how much load we have to carry in EDFC and how much load in WDFC, and the system has been designed to meet the practical requirement of 2031-32 basically. And these are the contracting strategy which has been adopted because DFC CIL has used FIDIC yellow book, and it has been customized for design build lump sum contracts for railway infrastructure works. So here it is PQ has been followed by single stage or two stage bidding, and new technology has been encouraged with the use of cross acceptance criteria to invite prospects of new vendors also. The design methodology which has been used, first we have carried out a traction power simulation study, which tells me about the sizing of the equipment, like what is the sizing of traction transformer, sizing of auto transformer, sizing of contact wire, sizing of quaternary wire. So all these details we have received based on the outcome of traction power simulation study. Next is the OHE pantograph interaction study. It has also been simulated to know what is the maximum temperature rise, how is the interaction of our OHE with pantograph, like that. And then the earthing and EMI study, because in this system of railway infrastructure, electromagnetic interference also plays a vital role, because in the same vicinity of electric wires, there are wires for the telecom network, mainly for system. So this is an important study, and this also has been carried out through the simulation and assuming a fault current of 12 kiloamperes. Next is the power supply arrangement, which have been adopted on ADFC and WDFC. In ADFC, there are total 19 substations and a spacing of around 60 km on double line and 90 km on single line. The 7 substations have been planned connectivity with respective discoms, whatever are the nearest discoms, and 12 substations planned with CTU connectivity. In WDFC, there are total 25 traction substations. Approximate distance is around 60 km. And in WDFC, all substations have been planned with discoms directly, mainly through open access basis. If we see the power supply installation, the parameters, the spacing is like 55 to 65 km, and switching posts are at 15 to 17 km. Auto transformer which has been used. The rating of traction transformer is around 60 MVA, upgradable up to 100 MVA in the OFAF mode. The switch gears have been designed for carrying higher current carrying capacities. These circuit breakers are SF6 based HV side and VCB for 25 kV side. Protection is fast acting intelligent numerical protection, and dynamic reactive power compensation has been used, because nowadays, as I was just listening, somebody was asking about the power quality aspects from NCRTC. So I can make it very clear that here DFCCI has been using dynamic reactive power compensation so as to ensure the power quality parameters, they are within the limits, and we do not pay a single penny of penalty on account of low power factor or any harmonics in the system. So DFCCI is taking care of all this with the adoption of this dynamic reactive power compensation. The OHE features, OHE has been designed as per EN 50119. Overhead aerial arc conductor is there, as is shown in this picture also. Buried arc conductor has been used for limiting the step and touch potentials as per the limits in International European norm 50122. Feeder wire is there, negative feeder all along the section. The droppers are current carrying and flexible droppers. It is not like Indian Railways where these are rigid and non-current carrying. Modular cantilevers have been adopted in a section of around 250 kilometers, just to gain an experience that how these, what are the benefits of these cantilevers in terms of maintenance, operation, and all. If these are found to be beneficial, then it can be adopted for the future corridors also. OHE design cylindrical foundation have been used based on UIC method. The steel structures, they are higher length because of high-rise OHE, because our MMD is at 7.1 meter level. So our OHE is also at 7.54 meter. Flexible droppers are used, and steel structures are suitable to support thicker conductors. Conductors, if you talk, our contact wire is copper alloy, battery wire is along copper alloy, 150 and 125 square mm basically. Feeder wire is triple AC. Aerial arc conductor, as per the earthing and design requirement. Buried arc conductor has been designed, and the critical values of these parameters has been based on mainly on the simulation study. So this alloy what has been used in quaternary and contact wire is mainly to withstand temperatures up to 100 degrees centigrade. So it also shows that we will be able to carry higher loads on our network, because the conductors sizes is more and their temperatures bearing capacity is also up to 100 degrees against normal temperature of 50 degrees Celsius. So this is just a picture showing high-rise OHE. Our high-rise OHE is at a height of 7.54 meter, which is suitable for double stack operation on WDFC. So this is probably first in the world at such a height of 7.54 meter. This is for the traction need for simulation, how we have carried out the simulation, traction power simulation, OHE pantograph simulation, earthing bonding simulation, which have used. And these are the outcome of this simulation. I will not have that much time to discuss probably, because these are the main features which we have gathered based on the simulation study in EDFC as well as in WDFC. These are the other OHE parameters details given here. So if we compare with Indian Railways, our system is entirely different, because in Indian Railways it is 25 kV and here it is 2 into 25 kV. Contact wire is different, catenary wire is different, feeder is different, earthing system is also different from IR, and our system is mainly complying with EN 50119 and 50122. Simulation study, Indian Railways is not applicable because the items are already standardized by RDSO, but here we have optimized the sizing of equipment based on the simulation studies. The traction transformer rating is against 21.6, here it is 60 MVA, means around 3 times the rating of the transformer. We are used 8 MVA auto transformer, not in IR. Metering arrangement is different. SCADA, here we are using the TCP IP protocol based on IEC 60870 open protocol. And for display, we are using a video wall in operation control center, which will be established at Ahmedabad, and one has been established in Allahabad. Part locator, it is not in use on IR, but we are using for fast localization of parts. So this is just a picture of cantilever, this modular cantilever which I have shown. These cantilevers are much lighter in weight and made of aluminum alloy, and easy to handle, easy to install, easy to replace basically. This is SCADA design, I already told. This is the video wall which we have provided. This is the actual video wall which has been provided in Operation Control Center at Allahabad, which will be controlling Eastern Freight Corridor. So this is a very big wall, and it shows all the systems on the screen itself, whether it is in electrical system or SNT system. The status can be shown on the video wall itself. So this is the power factor correction. I told in the beginning, this dynamic reactive power compensation, which is being adopted by WDFC, so as to avoid any penalty because of low power factor or because of injection of harmonics in the system. So our compensation range is from 0 to 5000 kVAR, which will be sufficient for the system design capacity level. These are the green initiatives adopted on WDFC and EDFC also. We are using SCADA for energy management. All B endorsed label products have been used. Smart grid we are creating for the DFCCC, and buildings have been complying with the necessary ECBC codes. These are the footprint of carbon emission. If we see that DFCC will be able to save around 457 million ton carbon dioxide emission over the 30 years period based on the traffic projections shown here. These are the targets and timelines of the different packages. One is EMP4 Rewari to Makarpura for electrical works. It is target is March 22. EMP16 is June 22. So these are the mainly timelines. If we see that by 30th June 22, all the corridors will be completed to a larger extent, and some projects, some corridors will be opening earlier, like Khurja Bhaupur in December itself, December 2020, and in Mughalsarai Sonnagar also by December 20. So we are opening the project in phase where Khurja Dadri June 21. So these are the upcoming tenders and opportunities. Right now, I explained we are executing 2 corridors, but now we have taken up 3 corridors: East-West corridor, Howrah to Mumbai, North-South, Delhi to Chennai, and East Coast, Kharagpur to Vijayawada. So out of these 3 corridors, the sections which have been taken for DPR, one is Bhusawal, Nagpur, Kharagpur, Dankuni, and Raj Kharswan to Andal. North-South, Vijayawada to Itarsi, and in East Coast it is Kharagpur to Vijayawada. So this is around 3,958 kilometers of sections, which for which DPR is already in the process, which we have awarded the tender for this DPR, and the work has already been started. The estimated construction cost will be in that range as of based on estimate of 2018. However, based on the DPR outcome, we will be able to finally conclude how much will be the estimated cost. And these are the upcoming tenders for the feeder routes, because as the western in the western corridors, there will be number of lines in Indian Railways which will also need to be augmented in terms of electrical infrastructure. Like they have to be electrified, they have to be electrified for high fitment of high-rise OHE, double stack containers. So these are the total routes where the works are already in the process, on around 1516 kilometer on western corridor, and eastern corridor it is around 3430 kilometers of different sections which are under progress of electrification. Just they will be feeding DFC CIL at different junction points. So this is what I wanted to say. Thank you very much for your patience hearing.